for those students here at BYU is to, if you're going to run this on, or when you're ready to run the optimization, set up, you can go ahead and do all this on a Windows computer and mesh and get everything set up like we did right now, and go ahead and run a check on your Windows computer. Once your check runs and it says it's good and it's ready to solve, just save your file and then go log into a Linux box and open it up and run it there, because the optimization will run much, much, much faster. When I did this lab, I ran the optimization and it took 7 minutes to do the optimization on this little part, which is actually a really long time for such a simple little tutorial. And on the Linux box, it took 1 minute. So you could save a lot of time if you just do that. However, we would suggest that not everyone always works on the Linux box, because there's not enough for everyone. So it would be best if the BYU students do all your work on the Windows machines until you're ready to run optimization, and then just jump over to the Linux box and do that, and then you can just jump back and look at your results. Okay, so we've completed successfully. It says there's no problems. It hasn't thrown any warnings, so that means we're good. So now if I change the run options to optimization, it will run that same check beforehand just to make sure, and then it will run the, yes, so I'm going to overwrite that file. Then it will run the optimization. So let's just pretend that we're on a cooking show and we're all done. Once it's done, it'll tell you that it's done, and then what you do is, if you close it, it'll recognize, since it has the file path pointing here, if you click Hyperview, it will then open those results files that you've created from that optimization in Hyperview, which is the program to view the results. So here I have Hyperview opened, and I'm trying to, let's see. So if I want to load these results, it'll take forever. Okay, so the results files we're looking at are H3D files. So those are the ones that we want. And in this case, since there were those three load cases, the break, the corner, and the pothole, it gave us 3 results files, 1 for each. So I'm going to click on this and say open. And this, if you click the Hyperview button in HyperMesh here, it'll just open all 3 of these already for you. But if you want to open up Hyperview later and look at results you've already seen, you can just open up it directly and do that. So here it's going to open up this file, and I'm going to click apply, and it doesn't take too long to view the results. I think I found where I made the mistake. Were you here earlier, Jared? I forgot to check a box on somewhere on the responses, so it was only doing X. So that's why I had that. Okay, so here's the results of the subcase 1, which is break. And so it has us, so it says so there's different pages. So this one only has 1 page because I've only opened 1, but I can, file, I don't remember how to open a new page. Let's just pretend I have other pages. Oh. And that'll be the results as well.
Yeah.
We'll open up all the pages though?
Should.
Okay.
Well,
that's the design. Yeah, that's what we want. So you can flip between the different pages. It'll have little arrows up here, and you can see and you can look at the different load cases and everything. So it has us basically take a look at the, so it'll have us take a look at the contour plot. So that's this button right here. That is kind of a rainbow. That'll give us a contour plot of our part, and especially with each load case. And you can see that the contour plots are different with each one. So if I go to contour plot, this is on iteration 0. This one might not have it because this is the design history one. So it'll have 4 H3D files. So 3 of those are the different load cases, and the 4th one is the design history one, which is the one we really care about to see the optimization, how it did. So this one will be, okay, so if you go to contour plot, it'll say result type. What do you want to show on the contour plot? And in this case, since this is the design history one, design, it won't let us do forces or stresses, but usually on the other ones you can pull up an element stresses and all that kind of stuff. So this one is element densities and density, and I just click apply, and now it will. So as you can see, this is the first. Another thing to mention, this is the first iteration. So the optimization, Dr. Jensen's probably lectured about this, but it runs a finite element analysis and takes that results and makes some changes to your part, and then it runs another one, and it runs another one. So this one has, I believe, so if I go back one, so down here it says iteration 0. If I go back one, it'll be iteration 22. So here it ran 22 iterations until it found the results, until it got this. So I'm going to do interpolate colors. Let's see what that does or not. And then you can also do, it has you do a deformed toolbar, and you can have it show you how much it's deforming according to each load. And then the last thing is, and you can even animate it with this button over here. And then we want to view an ISO view, which is the coolest part of this lab. So if we go to, it says graphics, and then ISO value, which is actually the same as this button right here. And then it will ask us what our result type is. In a minute. And we want to make sure that's element densities. And then we click apply. And that will give us our plot of ISO values. I guess. See, so this one was the one. It's actually won't look like this because this is. I forgot to check that box, that radio button that I mentioned earlier. So yours should look different, more like the picture, actually exactly like the picture. And so you can slide this bar, or you can also just set the value to be what you want. So it says to set it at 0.15. And that is our result there at 0.15. This is what this is. So that's basically it. Are there any questions about what I did so far besides just how do you do this or that? Okay, yeah, it's a lot, but ask questions, and we'll try to help explain why you have to do all this stuff.
Does anyone have any questions as to what this is or what this does? This ISO plot is merely showing where the loads go. It says you can remove most all of this material and leave these areas, and you should still be able to meet constraints. This one that he did know, because he didn't check one of the boxes. But the one in the picture on the tutorial, yes. The one that you'll make, it should look exactly like the one in the tutorial. One or two.
Well, my optimization didn't run correctly. It only took into account one of the the X direction and didn't take into account the other ones.
Yeah, so just one.
This is what it should end up looking like.
But later, you're going to take this part and model it back into an X. And that will allow you to add parameters to it to make the parts thicker or thinner depending on the actual loads you're going to use. Because this is only useful for saying where are the loads, not necessarily how big are the loads or how thick to make these parts. That comes later. Does that make sense? Cool.
Well, the element densities, what does that actually stand like? What does that actually tell you?
The algorithm that they use for optimization, when they run a finite element analysis on the entire part, it says, okay, where do we have higher loads? So then it sets these elements that have no loads to a density of 0. And so it does that over and over and over again, trimming down to next to nothing.
Okay, so that's a low density for like some volume.
Yeah, it just says, I want to trim out all the places with really low loads, but keep everything else. Or I want to trim out everything with less than half the load. Yeah.
Okay, so this finished. If you want to look at some of the things, you can also even open up. So here I have, this is where I've opened the part, and I'm going to refresh this, and now it has all these results files. These are from this is the optimization. As you see, they were just created right now. And so if you look at the .out file, that is the, if you open it with like Notepad++, this tells you all the results of, it goes through everything that it did. So at the bottom, it says it took 6 minutes and 50 seconds to do. So that's way too long. Anyway, so now, yes, I did. I went over that. So if I close, I'm going to close Hyperview here. And so now that it's finished that, I can click the Hyperview button like we were explaining earlier. And it will open all this stuff, all those H3D files into Hyperview so you can view them. And you can do the rest of the lab.
This is the easier way of opening Hyperview.
Yeah.
Once you finish the analysis, just click there, and it'll load all 3 files for you.
Okay. In that case, we encourage you guys to go ahead and get working on this. Besides this, we also in the lab. So once you do this tutorial, then what you want to do is start going through other parts on your car. Find a part, find some loads, and do optimization on that part as well. And so that's all explained in the lab handout. So encourage you to learn this stuff. It's a little bit, it's a lot to take in. I think OptiStruct is really cool because of everything it can do, and we're here to help. So ask any questions. Yes.
On the lab, the in-class part, all of it is referring to this part, right? When it says take it into NX and make a new design.
This down here.
Number 6.
Number 6, yeah.
So is that after we do the?
That's not creating a new part.
Right.
This is referring to parts for your actual car. Next lab will be taking the stuff from Hypermesh and putting it back in NX. This is just making something that looks kind of like your control arm per se, and but instead of modeling all the geometry inside it, just making one big block, a design space.
Just like a design space.
Yeah, and then you'll take that and put it into Hypermesh.
So, and then step 6 of the in-class is to take what Hypermesh created and put it back into
That's
NX.
next lab.
No.
Don't worry about taking stuff from Hypermesh yet.
6 is saying create your own thing, create your own part in NX, and then import that, the design space, kind of like,
Just a big block, a chunk of stuff
Okay.
with somewhere to tie to.
yeah, basically make this, but with your own part in NX, and then import that into Hypermesh and do the same thing on that.
Is there a requirement on our car how many parts to optimize?
Each person of the team has to do at least one optimization. Beyond that, it's preferable to do more. But in our team, when we did it, we had one person who was the specialist in optimization. Everyone did at least one optimization aside from this lab, but then that person did 2 or 3 more. Does that make sense?
So yeah, just to be clear on this, as a team, so one person from your team make the part in NX, and then everyone gets a copy of that part, imports it into Hypermesh, and then does this, and then does the optimization on it. So I would suggest, like when I did this, when I took the class, we all did it together. We did the same part, but individually at the same time. Does that make sense? So we were all going along the same steps, doing it together to practice that. And by the end, we all had basically exactly the same optimization. So, okay? All right.
Yep. We'll be walking around if you need help.
So, Eric, one question that I have.
Those of you on Skype, I am going to hang up the call now. So if you need any help, just call me back if you have a question and stuff. Okay? Okay. Bye. All right. What's up?
Question for you. So, the model that we import already has these little like gray things with nodes in them.
Right.
When we create our own geometry and import it and mesh it and all that sort of stuff, will we need to create these little?
Okay. The reason they made those is because it's the easiest way to put one constraint. I mean, we could put. Let me see. Yeah, so these RBE2s are rigid. They're perfectly rigid. So it's basically by putting one constraint and having rigids going to all these different nodes, it makes these nodes completely rigid. Does that make sense? I don't know how they set up these RBE2s. They might have some